Thanks for the introduction, and thanks for the opportunity to speak here. So I want to talk about the project which is part of my PhD, joined with my supervisor, Johan Makut, about the Poisson non-degeneracy of the Lie algebra SO31. And that fits within the framework of the question of linearization of Poisson structures and of normal forms. So the first part will be about recalling the things and giving an outline what is known at the moment. And the second part will be about the idea of the proof. So we start with a Poisson manifold, mmpi. And first we want to recall the well-known Weinstein splitting theorem, where, well, we have given a point P of the manifold, where the Poisson structure has rank 2n. And, well, the theorem says that locally around that point, we can identify the manifold with, well, the standard symplectic, with a neighborhood of the standard symplectic space around the origin, and another Poisson manifold, such that the Poisson structure pi m prime on this manifold is 0 at the point where the point P is mapped to. So that somehow it reduces the study of normal forms around the point to the study of normal forms of Poisson structures which vanish at the point. And the most basic example of such a structure is a linear Poisson structure, and linear Poisson structures correspond to Lie algebra structures in the following way. So if we have a Lie algebra structure, then we get the linear Poisson structure well, by this formula. So given an element of the dual of a Lie algebra xi and two elements of the Lie algebra xy, which we identify with the dual of the dual, then the Poisson structure is just given by the evaluation of the Lie bracket of x and y by the element xi. And, well, in local coordinates, this can be expressed in forms of the structure constants, where the structure constants define the Lie algebra and also the linear Poisson structure, and that's a one-to-one correspondence. Now, given a Poisson manifold, and the point where the Poisson manifold vanishes, there is a natural Lie algebra structure on the cotangent space of that point on the manifold, and it's defined in the following way. Well, we can represent every cotangent vector with the differential of a function. So the Lie bracket of two such elements is simply given by the differential of pi of df and dg evaluated at that point. And it defines a Lie algebra structure on the cotangent space of that point. And this Lie algebra has a special name. It's called the isotropy Lie algebra of pi at the point P. And, well, as we have seen in the example above, we can associate to a Lie algebra a linear Poisson structure on the dual. So in this case, it would be the tangent space. Well, in this associated Poisson structure is called the linear approximation of pi at the point. So, well, now a very natural question to ask would be, when can we identify the Poisson structure with its linear approximation around the point? And that's exactly the question we want to investigate. So given a point on our manifold where the Poisson structure vanishes, the question is pi linearizable at P, which is equivalent to finding a local diffeomorphism of the manifold mpi and the point which maps the point P to 0 in the tangent space, and which maps the Poisson structure pi to the linear approximation. Now, the answer to this question might depend on the Lie algebra, on the isotropy Lie algebra. And a Lie algebra is called Poisson non-degenerate if this question can always be answered positively. So whenever the co-isotropy Lie algebra is isomorphic to Lie algebra, then the answer to this question is yes. And, well, if that's not always the case, then we call the Lie algebra Poisson degenerate. However, the answer to this question might not only depend on the Lie algebra, but also on the category we are looking at. So one could ask, for example, this phi not to be a smooth diffeomorphism, but one could ask it, for example, to live in the formal category, so to be a local equivalence in terms of power series, or to be analytical. And, well, writing just by writing out what it means to be linearizable, one obtains some chromological abstraction. And well, it turns out in the formal category, for the case of semi-simple Lie algebra, these abstractions are always satisfied. So that was realized by Weinstein. And well, the result is any semi-simple Lie algebra is formally non-degenerate. Yeah, so which deals with the formal category. And a similar statement is true in the analytic category, which was proven by Kohn. So also for when we look at analytic transformations, then we have any semi-simple Lie algebra is analytically Poisson non-degenerate. So there should always be Poisson in there. Okay, so now we are turning our attention to the smooth category. And there the answer is a bit more subtle. So therefore we first recall the Iwasawa decomposition of a semi-simple Lie algebra. So any semi-simple Lie algebra decomposes into the K, which is the compact part of the Lie algebra, some abelian part A, and some nilpotent part N. And for us of special interest is A and the dimension of A, which is sometimes also called the real rank of the Lie algebra. And now, well, what is actually known is the following. So the first is when our semi-simple Lie algebra is actually compact. So if the dimension of A is 0, and that also implies that N is 0, so we only have G is equal to K. And then it was proven by Kohn that the Lie algebra of a compact type, the semi-simple Lie algebra of compact type is Poisson non-degenerate. And well, later a geometric proof of this theorem was given by Kreinig and Fernandez. So then for the case when the dimension of A is at least 2, so when the real rank is bigger or equal to 2, Weinstein showed that in this case G is Poisson degenerate, which leaves us with the case when the dimension of A is 1. And there we have to make another distinction. So if the dimension of A is 1 and the compact part is non-semi-simple, so the K is not semi-simple, then Monnier and Sung showed that in this case G is also Poisson degenerate. So one cannot always find a local equivalence. Okay, so which leaves us with the case where the dimension of A is 1 and the K is semi-simple, and well, that part is still conjectural at this moment. And the conjecture is that in this case, G is Poisson non-degenerate. So now, of course, in the title of my talk, I mentioned the Lie algebra SO3-1. So how does SO3-1 fit into this picture? And therefore, we look at its Iwasawa decomposition, and well, we use that SO3-1 can be identified with the real Lie algebra SL2C. So we view SL2C as a real Lie algebra, and then its Iwasawa decomposition is given as follows. So the compact part is just SU2, and then the A is given by this real diagonal matrices, and then the nilpotent is just upper triangular with complex some complex coefficient there. So we see that the dimension of A is 1 and SU2 is semi-simple, so the compact part is semi-simple. So it fits exactly in the conjecture. And well, in fact, it's the lowest dimensional example of the Lie algebra in this conjecture. And well, the statement we prove is that this Lie algebra is non-degenerate. So, well, and the way we do this is we basically use the basic idea of Kohn's proof, which of Kohn's proof for the compact case, which can be summarized as follows. So what we do is we show that the second Poisson chromology is trivial, and that we obtain some nice homotopy operators for the second degree of the Poisson complex. And then the idea is to apply some Neshmotze type of method to show that the Poisson non-degeneracy. So yeah, so that's basically the first part of my talk. And in the second part, I will somehow define or explain the three terms in this strategy of the proof a bit closer, which we haven't seen. So Poisson chromology, homotopy operators, and Neshmotze techniques. That will be the part of the second talk. Yeah. Are there any questions so far?
Maybe, Florian, just a quick question.
Yes.
So like so let's say in the cases where the situation is degenerate,
yes.
Can't you still say something sensible about the modular space of Poisson structures that linearize to that one? I mean, is there like something smart like that one can say even if there is degeneracy?
Well, so as far as I know, somehow this degeneracy condition is always obtained by somehow finding some second cohomology classes. But I think the problem is that, well, it's not clear if these are somehow all cohomology classes or not. And somehow the first step to answer the question would be to understand really what is the cohomology actually.
No, okay, I think that answers my question more or less. Okay. Yeah, thanks.
Okay, so let's continue with Poisson cohomology. So, well, Poisson cohomology is something which is naturally associated to every Poisson manifold. It's the cohomology obtained by the cochain complex, which is built by the multi-vector fields on the manifold, and the differential d pi, which is well defined in the following way. We have the Schouten-Nijenhuis bracket, which is some extension of the Lie bracket to multi-vector fields. And we plug in the first slot pi, and it gives an operator which increases the degree by 1 on the multi-vector fields. And the fact that pi is Poisson implies that it squares to 0. So this complex is actually a cochain complex, and we get a cohomology, which we call Poisson cohomology. And well, as mentioned in this, in the idea of the proof, a special interest is the second Poisson cohomology. Well, why is that the case? Well, so an heuristic interpretation of the second Poisson cohomology is the following. It governs the infinitesimal deformations of pi modulo the deformations one obtains by diffeomorphism. So a vanishing should correspond somehow to the fact that pi, all the deformations of pi are obtained by diffeomorphisms. Okay, so well, now we deal with a special situation somehow here, because we want to calculate the Poisson cohomology of a linear Poisson structure. And for this, there is also some Lie theory going, or one can see this also from a Lie theoretic perspective in the following way. So one can identify the complex of multi-vector fields with well, elements on the cochains on the Lie algebra with values in the smooth functions on the dual of the Lie algebra. So the differential turns into the differential into the Eilenberg-Chevrolet differential, which is obtained from the G representation given, well, as described here. So x acts on a function, on a smooth function f, using this linear Poisson structure. So in this way, for linear Poisson structures, one can see Poisson cohomology as Lie algebra coefficients with Lie algebra cohomology with coefficients in smooth function on the dual. Now, what is important for us is that somehow smooth functions can be somehow fit into the short exact sequence. So here on the left-hand side of this short exact sequence, we have the smooth functions which vanish flatly at the origin. So these are functions where all the Taylor polynomials are 0 at 0. And then, well, the short exact sequences are completed by, on the right-hand side, the formal power series, which are basically the Taylor polynomials at 0 of a function. So from this short exact sequence, we obtain a long exact sequence in cohomology. So here, H index 0 is the cohomology associated to the functions which vanish flatly at 0. Well, the standard H is the standard Poisson cohomology, and H index F denotes the formal Poisson cohomology.
Can I ask a question?
Yes, of course.
Why is this J0 infinity surjective? Because I would think that there would be power series that don't converge.
No, they always do. No, that's by the Borel lemma. You can always, like, given a power series, you can always extend it to a smooth function. With that power series at the point.
Yeah, it's smooth but not analytic. So that's the point.
Oh yeah, it's not analytic, but we are in the smooth case. Yes.
It's not about convergence.
Yes.
Oh, so it's an asymptotic expansion, not a Taylor series.
Yes, yes. So it's really something which is important for the smooth case. Yeah.
Thanks.
Okay, so we have this long exact sequence, and well, as one can show, is if the Lie algebra is semi-simple, then this long exact sequence becomes a short exact sequence. Well, corresponding to the short exact sequence we have for the functions. So we have the flat Poisson cohomology, the Poisson cohomology, and the formal Poisson cohomology. Okay, so now how do we obtain the Poisson cohomology? Well, the first step is actually to obtain Poisson cohomology using the short exact sequence by computing formal Poisson cohomology and flat Poisson cohomology separately. And for the formal Poisson cohomology, one can use some methods from Lie theory to calculate this. So which leaves us with calculating the flat Poisson cohomology, so the cohomology of the flat Poisson complex. So that's somehow step one. Now what we have is we have multivector fields which are flat at 0, and well, on SO3-1 somehow the foliation, the only singularity of the foliation is precisely at the origin. So basically what we have is multivector fields which are flat exactly at the singularity of the foliation, and that allows us to treat the subcomplex somehow as it came from a regular Poisson structure. And what we do then is we apply a spectral sequence argument. So spectral sequence argument is applied to the filtration, which is given by, well, one filtrates the multivector fields by the number of legs in the direction of the foliation. And the spectral sequence argument basically allows one to reduce the computation of the flat Poisson cohomology to the computation of what's called the tangential flat Poisson cohomology. So that would be the subcomplex of multivector fields which are tangent to the foliation and flat. And well, because all the leaves are symplectic, we have a correspondence between tangential multivector fields and, well, foliated forms. And usually that would cause problems because we are talking about a singular foliation, but because of this flatness at the singularity of the foliation, this allows us to somehow get the correspondence between the flat tangential Poisson cohomology and flat foliated cohomology. So in this way, we reduce somehow the computation of flat Poisson cohomology to flat foliated cohomology. And then for the flat foliated cohomology, we use something which we call a cohomological skeleton. So what is this? Well, so for the case of SO3-1, so we identify SO3-1, the dual, with SL2C as a real Lie algebra. And then this cohomological skeleton in this case is exactly the normal matrices somehow. So that's a smooth manifold away from 0, and this smooth manifold somehow intersects almost all the leaves in a submanifold which contains the cohomological information of that leaf, which would be in this case the intersection would be S2, because almost all the leaves are isomorphic to the cotangent bundle of S2. And while using the skeleton, we build a homotopy equivalence between the flat foliated cohomology and somehow a foliated cohomology on this cohomological skeleton. And there the computation becomes quite easy, let's say. So that's just a rough outline of what we're doing, and yeah, I will leave it at that due to time reasons. Okay, so well, in this way we can compute, in fact, the entire Poisson chromology of our Poisson manifold. What is important for us, however, is that the second flat chromology group is trivial. And what we additionally get from the computation are homotopy operators. So what are homotopy operators? Well, in our case, we just need them in degree 2. So we have functions from 3 vector fields to 2 vector fields and from 2 vector fields to vector fields. And they satisfy this homotopy relation. And well, this homotopy operation implies that H2 is trivial. But then in the main idea, well, we had this word nice homotopy operators. So what does nice mean for us? So in order to apply Neshmotze techniques, what one would want nice to mean would be the following. So X here is a multi-vector field in the right degree, such that HI can act on it. And then here the nth norm that refers just to the standard Cn norm. So, and what we require would be that the homotopy operator applied to X, the nth norm of it can be bounded by the nth norm plus some constant D. So that's also the estimates Con gets in order to apply the Neshmotze techniques. But unfortunately, that's not what we get. So in terms of the standard Cn norms, our estimate would look more like this. So the nth norm would be estimated by Q times n plus D. And in our case, Q would be, well, at least 2. And that somehow creates some problems when one wants to apply Neshmotze techniques, since, well, there are papers out there which show that Neshmotze only works for Q strictly smaller than 2. Yeah, so that's why somehow this we can't apply the standard Neshmotze technique somehow directly. But what we do is we look at the different type of norm, which corresponds more naturally to the flat vector fields which we are looking at. So we are looking at the following norms which have 2 indices. So the n somehow corresponds still to the derivatives, but now the k is something new. And well, this norm is defined in the following way. So the nkth norm is just, well, we take all derivatives up to order n, but then what we do is we multiply by 1 over the power of x to the k. And this norm is really only defined when one looks at the vector fields which are flat at 0, because otherwise it would explode. Well, and for the norms defined in this way, we obtain for our homotopy operators the estimates, well, as described here. And well, the important thing somehow is that the derivatives do not change too much. So where we get some additional, where it really increases would be the k term somehow. But somehow what we do in our proof is we show that the Neshmotze technique for such estimates can be still applied for this norms. Okay, so how do we show the linearization? Well, it's a two-step plan basically. So we have again our Poisson manifold mmpi and the point p, such that pi of p is 0. And well, in our case, we have the isotropy algebra to be isomorphic to SO3(1). So then one can first use the formal linearization of Weinstein and again the Borel lemma to get a local diffeomorphism which transforms into a Poisson structure pi tilde, which is still 0 at p. But now additional what we have is all its Taylor polynomials are the same as the ones from the linear Poisson structure at the point p. Okay, and then the second step is we apply Neshmotze technique in the flat setting to obtain a local diffeomorphism which maps this pi tilde to the actual linear Poisson structure. So, and how do we do this? That I want to explain in my last slide, which is about the Neshmotze technique. So I want to give a very brief outline of what this method is about. So somehow,
Sorry,
its
can I ask
origin,
you something before?
of course.
Yes, when you have this formal Taylor series, for example, you know that formally it satisfies the Jacobi identity, right?
Yes.
But then when you extend it to a smooth function, do you still, with Borel lemma, do you still know that it satisfies the Jacobi identity, this pi
But
tilde?
what you are extending is you extend somehow the power series to an actual diffeomorphism, and then all you do is you pull back the original Poisson structure using this diffeomorphism, because it's just like
I see.
Yeah.
What is formal is the diffeomorphism, not the Poisson structure. Okay.
Exactly.
Okay, thank you.
You're welcome. Oops, that was not planned. Okay, so now to the Neshmotze technique. So it's based on something which is very familiar to all of us, I guess, the Newton method. So we have a function and we want to find the zero of a function, and we start with a point which is, let's say, close enough to a 0, 1. And then what one does is one treats the function as it would be linear in order to get closer and closer to the 0. Well, by defining some of this iteration, which is given here. So xl plus 1 is given by xl minus f of xl divided by the derivative of f at xl. So therefore, one, of course, requires the invertibility of the differential. And somehow Nesh, based on this idea, Nesh applied or developed the following, which is now somehow a classical method for Frechet spaces. So, well, to somehow outline the idea in the classical setting, we take a differential operator, let's say from Cn plus 1 functions to Cn functions, and we have some function f0, which is n plus 1 times continuously differentiable. And we want the derivative of this differential operator to admit the right inverse locally around f0. And then one gets a similar statement. If somehow p of f0 is close enough to 0, then one can define again such an iteration which converges to a function where the operator is actually 0. But here we want to take a closer look at the right side, because if one would do that naively, one would get a problem, because the differential operator maps Cn plus 1 functions to Cn functions, and the right inverse then maps Cn functions again to Cn functions. So we would have somehow a loss of derivative here, so we cannot apply this iteration infinitely many times. So the idea of Nesh was to, well, very bluntly, put somehow a smoothing operator in front of this whole expression in order, well, to smoothen this whole expression out. So to get from a Cn function to a C infinity function. And well, quite remarkably, that idea works. And well, based on this Neshmotze technique, already Kohn used it in the setting of well, Poisson, or the linearization of Poisson structures. And the way we use it is now the following. So we recall from the part before. So now this pi here should be seen as the pi tilde. So we are just focusing on the second step. So this pi we have here has the same infinity jet at 0 as has the linear Poisson structure. So if we subtract the one from the other, what we get is a flat bivector field. And we also assume that this here is close enough to 0. And what we do then is somehow we define a vector field xl to be, well, we apply some smoothing operator to h1 of this expression. So here the h1 should be seen somehow as the right inverse r of fl here in this expression, and well, sl is still the smoothing operator. And then the way we define the iteration is the following. So phi of xl here is the time one flow with respect to the vector field xl. And phi of l plus 1 is just defined to be the pullback of this. And then what one can show is that this iteration here indeed converges to the linear Poisson structure. And the composition of all these time one flows of these vector fields defines a local diffeomorphism which does what we want. So the pullback of it maps this pi to its linearization. And well, that's already similar to what Con does, but Con does it only in the, like for on the entire complex of vector fields, not just on the flat ones. So what was the part here we added is that we really work entirely on the flat Poisson complex. So especially we needed to find here smoothing operators which map flat vector fields to flat vector fields. And then because we have these norms which have two indices, one needs to adapt the estimates a bit in order to obtain this two convergence statements. Yeah, that is the rough idea of how we prove this. And well, that is my talk. So thanks for the attention. And if you have questions, please ask.